The fundamental theorem of calculus opened a whole new world to mathematicians and scientists in the 17th century. Solutions to problems that had been nagging scientists and mathematicians were now easily solved. Hi, my name is Jason Rosenberry, and that's what today's lesson is going over. Let's start with the fundamental theorem of calculus, part 1, also known as the antiderivative part. If f is continuous on the closed interval from a to b, then the function capital F of x is equal to the definite integral from a to x of f of t dt. And that function has a derivative at every point x in the closed interval from a to b, and the derivative of capital F with respect to x will equal the derivative with respect to x of the definite integral from a to x of f of t dt, and that would equal f of x. Let's try this out. For this problem, we're being asked to find dy dx for two problems. The first problem is the definite integral from 0 to x of t cubed minus t, all of that to the 5th power dt. And the second problem is the definite integral from 2 to 5x of square root of u squared plus 1 over u du. So let's look at our first problem. We want to find dy dx, which is equal to d dx of the definite integral from 0 to x of t cubed minus t, all of that to the 5th power dt. So to find this, we simply take x and substitute it where we see t's over on the right hand side. So we're going to let t be x, and then we have to also evaluate dt, which would be simply the derivative of x with respect to x, which is just 1. So making that substitution, the t cubed now becomes x cubed minus t, we replace x for t, all of that to the 5th power. And now, since we're letting t equal x, dt is just the derivative of x, which we're just multiplying by 1. So our final answer is x cubed minus x, all of that to the 5th power. Let's try that again with the second problem. We would have dy dx equals d dx of the definite integral from 2 to 5x of square root u squared plus 1 over u du. So now we'll make that same substitution. We're going to let 5x equal u, or let u be 5x. So this would give us the square root, letting u be 5x. 5x, the quantity squared, would be 25x squared plus 1 all over, we're letting u equal 5x, so we have a 5x in the denominator, times the derivative of u. So if we let u be 5x, then du is the derivative of 5x, or just 5. So we're going to multiply by 5. These 5's divide out, and we're left with the final answer, square root of 25x squared plus 1 all over x. Let's try a slightly different example. Construct a function of the form y equals definite integral from a to x f of t dt plus some constant that satisfies the given conditions. We're going to make dy dx equal to the natural log of sine x plus 5, and also we're going to be told that y is equal to 3 when x is equal to 2. So again, here is our given information, and we want to find function y, and we'll find function y by finding the antiderivative of natural log sine x plus 5. Oh, my mistake. These functions need to be with respect to t, so we'll write it as sine t plus 5 dt. And we'll start with x equals 2, and we'll go to our from 2 to the upper limit of integration x. Now we have to also satisfy the fact that y of 2 got to equal 3. Well, what we currently have, that's not going to work. If you let x be 2 right now, we would integrate from 2 to 2, and we have a property that says that result would give us 0, and we need to have 3. So to address that, we simply put a plus 3 at the end of our answer. So we have y equals the definite integral from 2 to x of natural log of sine t plus 5 dt plus 3. Now let's take a look at part 2 of the fundamental theorem of calculus. This part is also known as the evaluation part. If f is continuous on the closed interval from a to b, and if capital F, or the antiderivative of f, is any antiderivative of f on that closed interval from a to b, then the definite integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Let's try some examples. Evaluate each integral using part 2, or the evaluation part, of the fundamental theorem of calculus. Here's our two problems. Definite integral from 1/2 to 3 of 2 minus 1 over x dx. And number 2, we will integrate from 0 to pi over 3 of 2 secant squared x dx. So let's look at our first problem. We first want to find the antiderivative of 2 minus 1 over x. So we'll do that term by term. The antiderivative of 2 with respect to x is 2x minus the antiderivative of 1 over x is natural log of absolute value of x. And we want to evaluate this expression from 1/2 to 3. So we will substitute the upper bound, upper limit of integration in the expression. So we plug 3 into the expression first. 2 times 3 is 6 minus natural log of absolute value of 3. We can just write as the natural log of 3. Minus what we get when we substitute 1/2 into the expression. 2 times 1/2 is 1 minus natural log of absolute value of 1/2 would just be the natural log of 1/2. And now we simplify. Here we have a positive 6, and here we have a minus 1, giving us positive 5. And negative natural log 3 plus the natural log of 1/2 can be simplified to minus natural log 6. So the answer to number 1 is 5 minus natural log 6. Number 2, we can start by, since 2 is a coefficient, we can pull 2 out in front of the definite integral. So this would equal 2 times the definite integral from 0 to pi over 3 secant squared x dx. And the antiderivative of secant squared x is tangent x. So our answer will be 2 times tangent x, where tangent x is evaluated from 0 to pi over 3. So our answer can be found by taking 2 times the quantity tangent pi over 3 minus tangent 0, and we would get 2 times the tangent of pi over 3 is root 3 minus tangent 0 is 0, giving us a final answer of 2 root 3. We can use the same procedure to use an integral to find area. Let's see how. Find the total area of the region between the curve and the x-axis. We're given the curve y equals x cubed minus 3x squared plus 2x, and we're looking at the closed interval from 0 to 2. Let's take a graphical peek at the area that we're being asked to find. Here's the graph of the curve, and we're being asked to find the total area from x equals 0 to x equals 2. We cannot simply evaluate the integral from 0 to 2 because that would cause the net area effect, where your area above the x-axis cancels out area below the x-axis. That's not how this problem is stated or worded. So what we must do is find the area from 0 to 1. We'll find this area. And then we'll find the area from 1 to 2, which is this area, and we will add those two areas together to find the total area. So here's our equation again, y equals x cubed minus 3x squared plus 2x from 0 to 2. So notice that we will first integrate from 0 to 1, and then we will integrate from 1 to 2. So let's do our first definite integral from 0 to 1 of x cubed minus 3x squared plus 2x dx. So let's first find the antiderivative. Taking it by each term, the antiderivative of x cubed would be x to the 4th over 4 minus the antiderivative of 3x squared. That's 3x cubed over 3. 3's would divide out, just giving us x cubed, plus the antiderivative of 2x would be 2x squared over 2, or just x squared. And we want to evaluate this expression from 0 to 1. So we'll substitute 1 into the expression first. So that's 1 to the 4th, or 1 over 4, minus 1 cubed, which is 1, plus 1 squared, which is 1, minus what we get when we substitute 0 into the expression. So substituting 0 gives us 0. So we get a total of 1/4. So that's the area from 0 to 1. That answer is 1/4. Now we'll evaluate the definite integral from 1 to 2. Now we'll find the area from 1 to 2. So we're going to simply change our limits of integration. They were from 0 to 1. Now we'll make that from 1 to 2. Same function. We would get the same antiderivative, but now we'll evaluate that antiderivative from 1 to 2. So now we first substitute 2 into the expression. So 2 to the 4th over 4 is 4, minus 2 cubed, 8, plus 2 squared, 4, minus what we get when we substitute 1 into the expression. So minus 1/4, minus 1 plus 1. And that looks like we get 4, 8, that's a 0, minus 1/4, giving us an answer. The answer to the definite integral is negative 1/4. It's negative because the area is below the x-axis. However, the problem does not want that. The problem wants the actual total area that we would have. So we had from the previous definite integral 1/4. This area, even though it's negative, the actual area is 1/4. So the total amount of area bounded by the curve and the x-axis from 0 to 2 would be 1/4 plus the previous 1/4, which is equal to 1/2. Now it's time for you to try a problem. Find the total area of the region between the curve and the x-axis. The curve is y equals 2 minus x, and the closed interval is from 0 to 3. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. So here's the graph of y equals 2 minus x. It's a line, and we want to find the area bounded between the line and the x-axis from 0 to 3. So here's x equals 0 and x equals 3. And as you can see again, we have area that is positive, and then we will have area that is negative. That change is happening at x equals 2. So again, we will need two definite integrals. The first one will go from 0 to 2. That answer will give us a positive value. That'll be the area. And then we will integrate from 2 to 3, which will give us a negative value. However, we want the area, so we would change that to a positive amount and then add those two amounts together. So our first definite integral will be from 0 to 2 of 2 minus x dx. So the antiderivative of 2 minus x with respect to x would equal 2x minus x squared all over 2, and we will evaluate that from 0 to 2. So substituting 2 in first, 2 times 2 is 4, minus 2 squared would be 4, 4 over 2 is 2, minus what we get when we substitute in 0, which would just be 0. So the result of our first definite integral would equal 4 minus 2 is 2, 2 minus 0 is 2. Now the next definite integral will be from 2 to 3 of the same function 2 minus x with respect to x. So we would have the same antiderivative of 2x minus x squared over 2, this time evaluated from 2 to 3. So substituting 3 in first, we would get 6 minus 3 squared over 2 is 9 halves, minus what we get when we substitute in 2, which we kind of did in the first definite integral, and when we substitute a 2 in, we got a 2. And so when we do the arithmetic, 6 minus 9 halves minus 2 becomes negative 1 half. Now that area is negative because it's below the x-axis. However, this question is asking for the total combined area, so we want to take positive 2 plus positive 1 half. So 2 plus 1 half is equal to a total area of 5 halves. In this lesson, we explored the fundamental theorem of calculus and its application. Be sure to work the exercises that your teacher assigns. We'll see you next time.